We just did an example in the last video of an infinite insulating sheet of charge. Of course, when I use the term sheet, I mean a very thin, large surface area. In textbooks, they'll often use the word plate when they mean it's a conductive material. A plate would be a very thin, large surface area, flat surface area that's conductive. And a sheet would be a very large, flat surface area that's insulating. But I don't always stick to that convention. Let's talk first about our insulating sheet and how the charge density is defined. On the left, I've shown a portion of an infinite sheet of charge that's perpendicular to the page. If we put some charge on that sheet, on one side of that sheet, we'll have a certain charge density. Now remember, we could try as hard as we can to make this really, really, really thin. But this sheet is always going to have some thickness to it. It always has some thickness to it. We can't make it one molecule thin. We can't make it that thin. It always has some thickness to it. So we're going to put some charge on one side of this insulating sheet, this surface. And, and it could be anything. Let's just call it 10 coulombs per square meter. We're going to put on that surface. Because this is an insulator, that charge has to stay on that surface. It can't go anywhere else. If I take out my knife and I cut a section out of the middle and remove it, a 1 square meter section out of the middle, it's got some charge on it. And if I could magically split it down the middle so that one side is over here and the other side is over here, there would be some charge over here on this surface. How much charge would there be on that surface? 10 coulombs of charge, because this is 1 square meter, and I know I put on this surface, I put 10 coulombs per square meter. How much charge would be on the other surface? Nothing. There would be no charge on that other surface because the charge can't get there. It can't move through the insulator. If I put it on the right surface, it's going to stay on the right surface. It's not going to move through to the left side. We can call this Q left, and this we can call Q right. Now let's think about what happens with a conductor. On the left, I've shown a portion of an infinite conductive plate. Of course, we try to make it as thin as we can, but we can only get it to a certain minimum thickness there. It can't get it to 0 thickness. There's always a little bit of thickness there. Now I'm going to put a certain amount of charge on this surface. As I add the charge to that surface, they are free, the charges are free to move around on that surface through the whole thickness of that conductor. It's a solid conductive material. Those charges all repel each other. If I put 2 positive charges on there, they want to get as far apart from each other as they can. And one way to get far apart from each other is to split. Half the charge will stay on one surface and half the charge will go to the opposite surface. So as I look at this infinite plate, half the charge I deposited stays on one side, half goes to the other side. So if I added 10 coulombs of charge per square meter to this plate, what's going to happen? I'm going to cut out a 1 square meter cross section, and I'm going to magically split it down the middle and look at each surface. And there's going to be some positive charges on this surface. How much? How much charge is on the right face of my sheet? 5 coulombs, because this is a 1 square meter section. Where's the other 5? It's on the other face here. So if I added 10 coulombs per square meter to one side of a conductive plate, half of that would jump to the other side, would move to the other side. I'd be left with 5 coulombs per square meter on this surface and 5 coulombs per square meter on this surface. They're equivalent. When I have an insulator with a sigma of 10 coulombs per square meter, it's equivalent in the amount of charge to a conductive plate that has a sigma of 5 coulombs per square meter, because I get double, I get 2 surfaces with the conductor, but the insulator I only get 1 surface. Let's see how this manifests itself when we find the electric field near a conductive plate. Here's a portion of an infinite conducting plate. It has a surface charge density sigma. That means on the right side, the right face of that plate, there's a charge density of sigma, and on the left plate, there's also a surface charge density sigma. Just like an infinite insulating sheet of charge, the electric field lines are going to come out parallel to each other, as I've drawn them here. We'll pick the same shape we did last time, a cylinder that's aligned, the axis of the cylinder is aligned with the electric field lines. We want the surfaces of our Gaussian shape to be perpendicular or parallel to the electric field lines. Here's our Gaussian surface. And we can see that we have some symmetry here, right? Our electric field lines are either going to be parallel or perpendicular to every face. Let's go ahead and use Gauss's law to figure out the electric field. The integral over every surface of our Gaussian shape of E dot dA is Q inside the Gaussian over epsilon naught. Of course, our Gaussian shape has 3 surfaces to it, so I can split this integral on the left up into an integral over the left side. What is the left side? That's this face right here. That's the left side of E dot dA plus the integral over the curved side plus the integral over the right side of E dot dA. The integral over the left side simplifies quite a bit because E is constant over that surface. So it comes out of the integral. E is normal to the surface, so is our area vector. So we get a cosine of 0 degrees, or 1. And we have the integral of dA gives us A, the area of that side. The curved surface has no flux. No electric field lines penetrate that surface. Or we have a cosine of 90 degrees, if you want to think of it that way, because our electric field is parallel to the surface, but the area vector is perpendicular to the surface, so we get a cosine 90 degrees, which gives us 0. And the right face also gives us E times A. And that's equal to Q in over epsilon naught. So just like last time, we're getting similar results as to the insulating sheet. But here is where it changes. We want to find Q in. Q in is on this face, the right side, where the right face is intersected by our Gaussian cylinder. But there's also charge on the other side, on the left face, here, where the left side is intersected by our Gaussian. So Q in is going to be the area times sigma times 2. And so I get 2EA is 2A sigma over epsilon naught. And I get the electric field near our conductive plate is sigma over epsilon naught. It's off by a factor of 1/2 from our answer last time with the insulating sheet, because sigma is defined a little differently. If both surfaces have the same amount of charge, you're going to get the same electric field. If you come back up here and see, if you really have 10 coulombs per square meter on your insulating sheet, and you have 10, like I do here, 10 coulombs per square meter on your conductive sheet, you're going to get the same electric field. It's just that the sigma is different for the insulator as it is for the conductor, because sigma is charge per unit area, and we have to look at only one side of our sheet or plate. We can't count the area on the opposite side also. I hope that's clear. That's our electric field outside of a conductive plate.